Hi, I'm Brandon Lynch,
And my name's KV Lay.
and today we're going to be talking about the Nintendo Entertainment System, also known as the NES. So, first, we're going to go over a quick overview of the history of the console. So, it came out during a difficult time. The video game crash in 1983 was a large recession in the video game industry. What had happened was the market became oversaturated with game consoles, many of which were poor quality, which plummeted the reputation of game consoles. And furthermore, the interest in games was shifting away from consoles towards PCs. The market did recover after a few years, in part due to the widespread success of the NES. Um, so in 1983, the NES was actually originally released as the Famicom in Japan. It wasn't called the NES until it was redesigned and released in 1985 for American test markets, soon coming to the rest of North America and Europe. The hardware inspiration for the NES came from arcade games. The devs mentioned a few games by name: the Galaxian, Donkey Kong, and Radar Scope. These games were noted for their powerful sprite rendering and scrolling capabilities.
During the 70s and 80s, the CPU market was really diverse, especially with the personal computers becoming more popular, as we said before. But Nintendo needed a CPU that would provide good performance but was affordable. And so, in the end, they went with a 6502 compatible chip. At that time, the 6502 design was not compatible with most things, and it was but it was really cheap, and this allowed Nintendo to mass produce the NES. And this also made the 6502 more popular in the market. And since Nintendo was also making a console, it didn't really need that compatibility, so it took full advantage of that fact, making this system. And developing for the NES, even though it was a well regarded piece of hardware at the time, it did have limitations, especially in compute and memory, forcing these programmers to shave off as many cycles they could and conserve memory in any way they could. And this led to very clever encoding schemes and ways to extend the system in ways today we might not think about. And the NES was conducive to that type of thinking. And now we'll be talking about the machine, starting with the CPU. And as we said, it's a 6502 based CPU called the Ricoh's 2A03, and it was an 8-bit CPU. It had 56 machine code instructions with 2 to 7 cycles per instruction. It also included a system stack, allowing interrupts to happen to save state and return back so that you don't lose any type of information. There's also a program counter that's 16 bits. There's a accumulator register that acts as a place to store results, kind of like the RAX register on x86. And there's two buses on the CPU, that being a 16-bit address bus and a 8-bit bidirectional data bus. The former indicating what the CPU is communicating with and where, and the latter specifying the byte being read or written to. There's also many CPU addressing modes. Something special about the NES CPU was that there's X and Y registers called indexing registers. They could store a value that can be incremented or decremented with special instructions or transferred from the accumulator register. However, it cannot be directly written to from the ALU from operations. And as you can see here on the right, there's these textbooks memory addressing modes, and on the left side you can see it kind of parallels with the NES addressing modes, but the NES has kind of their special X and Y indexing. As for CPU interrupts, there's three main kinds. The first one being reset, the next being non-maskable, the next being general external interrupts. And so these are ordered in terms of priority, where the reset interrupt is the most important. And this only occurs during startup because at that time the CPU is in an indeterminate state, and Nintendo wanted to make sure the right things were being run, and this reset always runs the same way. The non-maskable interrupt runs is just like the reset interrupt, but it just you're able to redirect what is being run during that interrupt. And this sets and clears the break flag just like the reset interrupt. And it saves execution context, of course, so that you don't lose information. The general external interrupt is the lowest priority, and the break bit is not set when you do this interrupt, so that this can be disabled through software means, which we'll see later. in the status registers. These are bit flags, just like the ones we learned in the book. The common ones, of course, being negative results, overflow, carry, zero results, all the usual. And there's also the interrupt disable, which what we talked about before, the IRQ uses, and a break bit, which indicates if a program has been interrupted in a hard way, in a sense.
Next up is the PPU, which is the picture processing unit. Images in the NES are constructed from 8x8 pixel tiles, and each tile is drawn using patterns from a pattern table that we see here, and they're colored using a 4-color palette that's chosen from a palette table. And there's two distinct layers in the image construction, the background layer and the sprite layer. And constructing a background layer requires 4 fetch cycles, which we'll go through now. The first cycle is fetching the name table, which we saw before this is kind of the table that puts together the puzzle pieces that are set up in the pattern table. And cycle 2 fetches the attribute table, which tells you which color palette to use for a square, and each square contains 4 tiles. Um, Cycles 3 and 4 fetch the pattern table, and this is like the puzzle pieces that will be put together by the name table. And to show a quick example of how the pattern table is used, if we look at the first row, there's a 1 bit in the 4th position in the upper half of the pattern table, and in the lower half of the pattern table in the first row, it's all 0 bits. So for the color result, the first row will be just a 1 in the 4th position, and that will represent picking the color number 1 from the color palette that was chosen. Next for the output, the 4 bytes of data that were fetched from the 4 cycles are loaded into 16-bit registers in the background buffer, and each pixel clock cycle, the registers shift 1 bit to the right, and the scroll bits represent the alignment of the tiles in relation to the edge of the screen. So if in the game the background is scrolling, this is how that happens. And so the scroll bits will select the necessary bit from the register and send that information to the background output. Next up is the APU, which is the audio processing unit. There's 5 audio channels, 2 of which are pulse channels, and pulse waves produce the distinctive beep sounds unique to retro games. The first pulse channel is used for melodies, and the second for accompaniment. But if the game needs sound effects, the second will be hijacked to play the sound effect and then returned back to the accompaniment. The triangle wave produces a bass line. Channel for noise produces ambient sound or white noise, but it can also be used for percussion if used in short bursts. And there's also a sample channel, which will play recorded media, but at a limited 7-bit resolution. One option would have been to stream 7-bit audio, but this would be very expensive for the NES. And so instead, the audio channel uses delta modulation to encode the change between one cycle and the next in the audio. And this is much cheaper, but it comes with the loss of accuracy and flexibility with the sample media. And additional channels, audio channels, can be added, but only in the Famicom, the Japanese version of the NES. There are extra pins in the cartridge slot that game devs can take advantage of by using expansion chips in their game cartridge to add more audio channels. One example of them doing this is in Castlevania 3. The music in the Japanese version has a lot more depth to it because they added a few audio channels compared to the American version of Castlevania 3. And here are some APU registers. We can see that we see the 5 channels that I mentioned before. And if we take a closer look at the pulse channel, we can get some insight on how it works. There's 2 duty bits which select the pulse width. There are 4 different pulse widths that come from the 2 bits. And then the sweep unit, um, there's an enable bit and then a period bit, which determines the length of the period, and then a negate bit, which lets you add or subtract from a period. Adding creates a lower frequency, and subtracting will create a higher frequency tone. And the shift bits, which tells you how much to shift the period um, to make it smaller or larger and adjust the tone.
Next, we'll be talking about memory, and as stated in the CPU section, there's an 8-bit data bus and a 16-bit address bus, allowing theoretically up to 64 kilobytes of memory access. When connecting a game cartridge, there's a bus on the game cartridge that essentially connects the cartridge memory to the CPU. However, the way Nintendo wired up the system, only around 50 kilobytes of the cartridge data can be accessed by the CPU. However, to circumvent these limitations, developers came up with the idea of mappers, which could be added to the game cartridge to facilitate more memory access. And so on the bottom left diagram, you can see there's a mapper that maps to the program memory, and by switching lines when you need to, you can access different parts of memory so that you can go beyond the 50 kilobytes of cartridge data, the limit, without this mapper. And this is one of the ways that developers find clever solutions to surpass the limitations of the NES. And so here on the bottom right, there's just address ranges and what these address ranges are assigned to for the NES. The first one from would be system RAM, and there's a couple for PPU registers and I/O registers, so on and so forth. The last part of this section would be I/O. There's the one to talk about is NES controllers. The NES allows up to 2 controllers that can be queried at registers 4016 and 4017. The second bit at these addresses indicates the connection, 0 being it's connected, 1 being it's not connected. So that might be a bit backwards for some. However, to get the information about the controller itself, you don't actually read the rest of the bits. You actually just read the first bit 8 times in a row to get the status of A, B, select, start, up, down, left, and right, respectively. You need to do like a special reset process first before you read this, but after that, you read it 8 times in a row, and every subsequent time, it's the status for the next button, which is a way to save memory on Nintendo's part, so that you don't have to use the whole address space. The other bits aren't actually used commonly, but it does allow for extension for like more complex controllers to write to those spots if ever need be. And thank you for listening to our presentation.